In this video we will calculate the voltage of this half cell. EMF stands for electromotive force. The way this notation works is that you have your anode, which is the site of oxidation. So we have magnesium solid going to magnesium plus 2. These two lines represent what's called a salt bridge. And then after the salt bridge, which are those two lines, we have the cathode. So anode, salt bridge, cathode is the way it works. In a cathode, we have the exact same thing, except it's in reverse. We have magnesium plus 2 going to magnesium solid. The magnesium plus 2 is in 0.53 molar. So on the anode side, the magnesium plus 2 is 0.24 molar. On the cathode side, the magnesium plus 2 is 0.53 molar. Okay, so the anode, salt bridge, cathode is the way this thing works. So let's go ahead and write out our anode. They're going to be the same, actually. So same voltage, except they'll be different signs. So magnesium solid going to magnesium plus 2. Here we lose 2 electrons. So magnesium solid going to magnesium plus 2. It's the flip of this. Magnesium solid going to magnesium plus 2. So we flip that equation and it's going to be positive 2.37 volts. Okay, so I'm going to label this the anode reaction. And in the anode reaction, the concentration they tell us here is 0.24 molar. Now let's do the cathode, which is going to be the reverse. It's going to be Mg plus 2 going to Mg solid, And here, to balance the charge, we have to gain 2 electrons. And as before, it's going to be the same value but opposite sign. Mg plus 2e minus going to Mg solid. It's the exact same thing. So we keep the value of minus 2.37 volts. This is the cathode where you gain 2 electrons. 0.53 molar for the cathode. So 2 electrons cancel. This from the product side cancels with this from the reactant side. So you're left with Mg plus 2 from the cathode, which is 0.53 molar, plus Mg solid. By the way, the Mg solids cancel also, just so you know. Goes to Mg plus 2. This is from the anode, which is 0.24 molar. So the Mg solids cancel. So here we have Mg plus 2, 0.53 molar, going to Mg plus 2, 0.24 molar. Okay? And the E cell here, when we add the anode site of oxidation with the cathode site of reduction, is 0.00 volts. Okay? So let's use the Nerst equation here. Here our Q is the concentration of Mg plus 2 divided by the concentration of Mg plus 2. Here in the numerator is the concentration of Mg plus 2 from the anode. I'll label that An. And on the reactant side, products over reactants is the concentration of Mg plus 2 from the cathode. I'll label that CaTH. Alright, so 0.24 divided by 0.53 will be our Q. So doing that on our calculator, getting about 0.45, let's add some extra digits here, 0.4528. And now let's use our Nerst equation. Remember, our Nerst equation is E under non-standard state conditions equals E of the cell under standard state conditions, 0.0257 volts over N. This is a 2-electron transfer reaction. 2 electrons are being transferred. Magnesium solid loses 2 electrons. Magnesium aqueous gains those 2 electrons times the natural log of Q. Okay. So E cell we already figured out is 0 volts minus 0.0257 divided by 2. Natural log of Q is 0.4528. So doing that on our calculator will give us EMF. EMF stands for electromotive force, as stated before, which is the voltage of this magnesium cathode, magnesium anode sort of combination under non-standard state concentrations. So natural log 0.4528 times 0.0257. We have a minus here, so to take into account we have to put the minus, so the minus into minus becomes plus. Don't forget divide by 2, and that plus is 0 gives us our final answer of 0.0102 volts. So very interestingly enough, if you have magnesium solid with magnesium ion, one can be the cathode, one can be the anode, and you can actually get a battery, very weak battery, of about 0.0102 volts.